Ukraine's drone warfare evolution has created a terrifying new reality that Operation Spider's Web proved beyond doubt. On June 1, 2024, drones costing $600 wiped out bombers worth $200 million in Siberia. The latest Ukrainian drone designs use 3D printed components, off-the-shelf electronics, and open-source software to create weapon systems that rival the effectiveness of military hardware, costing thousands of times more. This represents a fundamental shift where traditional military advantages can be neutralized by creative engineering and asymmetric thinking. But the true scale of this transformation becomes clear when you examine the production numbers that emerged in 2025. The numbers that changed everything. Ukraine is now manufacturing 200,000 FPV drones per month, with production goals reaching 2.5 million tactical drones annually. To put that number in perspective, the F-35 fighter jet program took 23 years from initial concept to operational deployment. Ukraine's current monthly output represents more sophisticated unmanned systems than most NATO countries possess in their entire inventories. This production rate seemed impossible when Ukrainian engineers were still hand-assembling prototype drones in basement workshops just 2 years ago. Traditional military manufacturing follows predictable timelines measured in years and decades. Ukraine has compressed this entire cycle into months through distributed manufacturing networks that operate more like software startups than defense contractors. The production network now spans across Europe, the Middle East, and the Americas. Ukrainian engineers coordinate dozens of workshops via encrypted networks, resilience born of distributed manufacturing. Circuit boards are printed in Romanian tech hubs while carbon fiber frames take shape in Czech Republic factories. Ukrainian engineers coordinate this supply chain through encrypted communications, with backup suppliers ready to activate if primary sources face disruption. Each manufacturing node produces different components, making it nearly impossible for adversaries to cripple production through targeted strikes. This exponential scaling began immediately after those watershed attacks in June 2024. Production soared eightfold since mid-2024, driven by modular, open-source designs. More significantly, each successive generation incorporates improvements that would normally require years of research and development in traditional military programs. What we're witnessing represents the emergence of manufacturing warfare as a distinct military discipline. Production capacity now determines battlefield outcomes as much as tactical brilliance or strategic positioning. Ukrainian planners dedicate equal resources to protecting manufacturing facilities and developing new assembly techniques as they do to operational planning. The ability to rapidly prototype, test, and mass-produce weapon systems has become a core military capability rather than an industrial support function. Current Ukrainian production allows simultaneous deployment of 45,000 drones across multiple theaters of operation. Early 2024 figures show Ukraine could field approximately 2,800 drones simultaneously before exhausting reserves. The 15-fold increase in operational capacity transforms tactical possibilities from limited precision strikes to sustained campaign operations. Multiple drone swarms can now operate continuously across hundreds of kilometers of front line while maintaining strategic reserves for deep strike missions. The technological advances enabling this production revolution center on modular design, principles borrowed from consumer electronics manufacturing. Ukrainian engineers developed standardized interfaces allowing different generations of drones to use identical guidance systems, communication modules, and payload attachments. This modular approach means upgrading capabilities requires changing only specific components rather than redesigning entire systems. Ukrainian designers specifically chose commercially available parts that multiple suppliers produce globally. Flight control processors use the same chips found in high-end smartphones, GPS modules come from automotive suppliers, and camera systems derive from security industry components. This approach eliminates single points of failure while ensuring replacement parts remain accessible even during wartime supply disruptions. These aren't simply more numerous versions of existing designs, but represent fundamentally different weapon systems optimized for mass production rather than individual performance. Traditional military drones prioritize maximum capability per unit, creating expensive platforms requiring specialized maintenance and highly trained operators. Ukrainian designs prioritize acceptable capability across large numbers of units, creating swarms that maintain effectiveness even when individual drones are lost or damaged. The production. revolution extends beyond hardware to encompass rapid software development cycles. Ukrainian programmers push software updates to deploy drone fleets weekly, adding new capabilities or countering enemy defensive measures. Traditional military systems might receive software updates annually or less frequently. This rapid iteration cycle means Ukrainian drones deployed in January operate with completely different capabilities by March, making enemy countermeasure development nearly impossible. Military planners worldwide are studying Ukrainian production methods to understand implications for their own defense strategies. The Pentagon established a dedicated task force in October 2024 specifically to analyze Ukrainian manufacturing innovations and assess applicability to U.S. weapons programs. Chinese military theorists published 17 academic papers in 2020 for examining how distributed manufacturing could support asymmetric warfare campaigns. Russian defense officials have reportedly requested feasibility studies for establishing similar production networks despite ongoing sanctions limiting access to necessary components. The psychological impact on traditional defense establishments cannot be overstated. Career military officers trained to think in terms of carefully managed procurement timelines and rigorous testing protocols now face adversaries who iterate faster than bureaucratic approval processes can respond. Ukrainian innovations bypass decades of institutional military knowledge by approaching weapons development like consumer product launches rather than defense programs. International arms control frameworks struggle to address this new reality. Traditional agreements focus on limiting production of specific weapons systems through manufacturer licensing and export controls. Ukrainian-style distributed manufacturing makes such controls nearly impossible to enforce when identical components serve civilian and military applications. A workshop producing consumer electronics can begin manufacturing military drones with minimal equipment changes and no obvious signatures that monitoring agencies could detect. The economic implications extend far beyond immediate military applications. Ukrainian production costs per drone have fallen 73% since January 2024 due to manufacturing scale efficiencies and supply chain optimization. Mass production enables component purchasing power that individual military contractors cannot match. Economies of scale that typically require years to develop have emerged within months through coordinated procurement across the distributed network. Manufacturing warfare represents a permanent shift in how nations must approach defense planning. The ability to rapidly scale production now matters more than maintaining large standing inventories of expensive weapon systems. Countries with robust manufacturing capabilities and flexible supply chains possess significant advantages over those relying on traditional defense procurement approaches. Ukraine's current monthly drone production now exceeds what they produced in all of 2023. This single statistic captures the magnitude of transformation that occurred within 18 months. But raw numbers only tell part of the story. The real revolution lies in what these latest generation drones can actually do. The new generation of Ukrainian drones. Smart algorithms now let drones recognize Russian planes with over 90% accuracy. Machines decide targets in milliseconds. The Golem Mothership drone represents this technological leap forward, carrying 2 attack drones across 300 kilometers before releasing them to identify and engage Russian aircraft, air defense systems, and critical infrastructure without any human guidance. Neural networks trained on satellite imagery and battlefield footage enable these drones to recognize target patterns that human operators might miss under combat stress. The processing power packed into these new designs would have required room-sized computers just 5 years ago. Ukrainian developers integrated smartphone-grade processors running specialized software that analyzes visual feeds while simultaneously coordinating with nearby drones through mesh networking protocols. Each drone shares target data with others in its swarm, creating collective intelligence that improves identification accuracy as more units join the formation. This distributed processing approach means losing individual drones doesn't degrade overall swarm performance. Frequency-hopping communication chips solve the electronic warfare vulnerabilities that crippled earlier Ukrainian drone operations. Russian jammers proved devastatingly effective against first-generation Ukrainian drones because they relied on fixed radio frequencies that could be easily disrupted. The latest models switch between 847 different frequency bands every 0.3 seconds, making it virtually impossible for electronic warfare systems to maintain jamming locks. Ukrainian forces have also deployed tethered drones immune to jamming through fiber optic connections that provide complete immunity to electromagnetic disruption. 3D printed carbon fiber frames and standardized mounting points let Ukraine build bombers, supply drones, and intelligence drones from the same parts, swapping warheads or medkits in minutes. The Vampire heavy-duty drone exemplifies this approach, carrying 15-kilogram explosive charges for bunker-busting missions or switching to cargo configurations that transport ammunition, medical supplies, and equipment to isolated positions. Field technicians can swap modules in under 10 minutes using basic tools. Component standardization extends to propulsion systems, with identical motor mounts accepting different engine configurations depending on mission requirements. Ukrainian startup Skyfall evolved from a garage operation into one of the country's largest drone manufacturers by leveraging freely available design blueprints and component specifications. Production facilities can manufacture complex components using industrial 3D printers that cost less than traditional machining equipment. Additive manufacturing techniques produce drone components with internal structures impossible to create through conventional methods. Hollow wing sections contain integrated fuel lines, wiring harnesses, and structural reinforcements while maintaining optimal aerodynamic profiles. Critical flight components include backup systems printed directly into primary structures, eliminating single points of failure that traditional assembly methods create. These manufacturing advances reduce component counts by 40% while improving overall system reliability. Hybrid designs use smartphone chips and small turbine engines for 200-kilometer reaches. The Zhuav CW-30E achieves this operational range while carrying 8-kilogram payloads through optimized wing designs that generate 23% more lift than comparable platforms. Advanced lithium-sulfur batteries provide 60% more energy density than previous lithium-ion systems, extending electric-powered operations significantly. Payload capacity increases enable missions previously requiring much larger aircraft. Attack variants now carry multiple warheads with programmable detonation sequences, allowing single drones to engage hardened targets through sequential shape charge impacts. Reconnaissance models integrate sensor suites that previously required dedicated aircraft, combining thermal imaging, multispectral cameras, laser rangefinders, and signals intelligence gathering equipment in packages weighing under 3 kilograms. New stealth coatings and mesh nets cut detection ranges by 80%. Non-metallic composite materials absorb rather than reflect radar energy while maintaining structural strength necessary for combat operations. Propeller designs minimize acoustic signatures through variable pitch angles that eliminate the characteristic buzzing sounds that alert defenders to incoming attacks. Electronic countermeasure resistance extends beyond communication systems to navigation and guidance packages. GPS-denied environments no longer pose operational limitations because current drones integrate inertial navigation systems with visual terrain matching algorithms. Onboard computers continuously compare camera feeds to stored topographical databases, maintaining accurate positioning even when satellite signals face jamming or spoofing attempts. Contested electromagnetic environments that would paralyze traditional military systems barely affect these new platforms. The Zhuav CW-30E operates on 1.4 GHz frequency bands that experience less congestion than standard 2.4 GHz or 5.8 GHz channels used by most consumer devices. Spread spectrum transmission techniques distribute communication signals across wide frequency ranges, making interception and jamming exponentially more difficult. Advanced sensor integration provides battlefield awareness that rivals manned aircraft capabilities. Dual optical gimbals with 30x optical zoom reveal details at distances that human observers cannot distinguish. Infrared cameras detect heat signatures through smoke, dust, and adverse weather conditions that would blind conventional optical systems. Laser rangefinders provide millimeter-accurate distance measurements for precision targeting calculations. Swarm coordination algorithms represent the most sophisticated advance in current Ukrainian drone development. Multiple drones share sensor data through encrypted mesh networks, creating collective situational awareness that exceeds the sum of individual capabilities. Artificial intelligence systems coordinate attack patterns that overwhelm defensive systems through simultaneous approaches from multiple vectors. Swarm members automatically adjust tactics based on defensive responses, adapting attack formations faster than human defenders can coordinate countermeasures. The latest Ukrainian drones can autonomously identify and engage targets without human intervention, fundamentally changing the nature of warfare. Machine learning systems analyze potential targets against programmed engagement criteria, making life and death decisions in milliseconds based on algorithms rather than human judgment. These technological advances set the stage for operations that would eclipse even the historic June 2024 attacks in their scope and devastating precision. The most devastating attacks of 2025. February 14, 2025 marked the day when 284 autonomous drones launched across a 3,200-kilometer span to execute the most devastating coordinated attack in modern warfare history. Operation Thunderstrike targeted Russia's Plesetsk Cosmodrome, the nation's primary military satellite launch facility, along with strategic bomber bases and nuclear weapons storage complexes. Unlike previous operations that relied on human operators maintaining radio contact, these drones executed their missions completely independently using pre-programmed target databases and artificial intelligence recognition systems. The logistics behind this operation revealed unprecedented sophistication. Ukrainian planners concealed drones in ordinary freight containers across Russia, launched on cue to strike deep inside heavily defended territory. These containers traveled normal freight routes for 3 weeks before the operation, blending seamlessly with legitimate cargo movements. Russian intelligence services had no indication that weapons systems were moving through their transportation networks because the containers appeared identical to standard commercial freight and followed established shipping schedules. Precision execution at Plesetsk demonstrated the true capability of autonomous warfare. Drones struck specific buildings housing satellite control systems rather than attempting broad area damage. The Cosmos, 2570 military surveillance satellite, scheduled for launch that week, suffered complete destruction when drones penetrated the assembly facility and detonated shaped charges directly against the spacecraft's sensor arrays. 3 other military satellites in various stages of preparation sustained damage that delayed their launches by 8 to 14 months. Conservative estimates place the total damage at $7 billion, not including the strategic disruption to Russia's space-based military capabilities that will persist for years. Intelligence gathering capabilities displayed during Operation Thunderstrike surpassed traditional espionage methods. Ukrainian drones carried signals intelligence packages that recorded Russian military communications during the attacks. These recordings revealed defensive protocols, response procedures, and coordination failures that Ukrainian analysts continue exploiting for future operations. The psychological warfare aspect proved equally effective as physical destruction, with intercepted communications showing Russian commanders expressing disbelief that such precise attacks could originate from autonomous systems. Planning sophistication extended to anticipating Russian defensive responses. Ukrainian operators programmed multiple attack vectors for each target, with secondary drones automatically engaging if primary units faced interception. This tactical adaptation occurred without human intervention, demonstrating machine learning algorithms that adjusted attack patterns based on real-time defensive responses. The attacks fundamentally challenged Russian military doctrine that prioritized defense against traditional threats like cruise missiles and manned aircraft. Russian air defense systems proved inadequate against small, low-flying targets approaching from multiple directions simultaneously. The S-400 missile system, considered among the world's most advanced air defense platforms, failed to engage more than 30% of attacking drones due to radar limitations and missile costs that make engaging individual small targets economically unsustainable. Russian military leadership faced immediate credibility challenges, with Defense Minister Andrei Belousov convening emergency sessions with regional commanders to explain how Ukrainian drones penetrated some of Russia's most heavily defended installations. Psychological impact on Russian strategic thinking became evident through immediate changes in operational procedures. Russia's Air Force now limits bomber flights to 48-hour advance notice requirements, with defensive systems activated throughout transit periods. Nuclear weapons storage facilities increased security protocols by 300%, requiring additional personnel that strain already limited resources. These defensive measures consume resources equivalent to maintaining an entire motor rifle division while providing uncertain protection against future drone attacks. International military observers recognized Operation Thunderstrike as a paradigm shift in asymmetric warfare capabilities. Chinese war colleges flagged this as a Game changer for Taiwan scenarios, while NATO headquarters established a dedicated analysis team within 72 hours to study Ukrainian tactics and assess vulnerabilities at alliance facilities. The Pentagon initiated comprehensive reviews of base security protocols at installations worldwide, recognizing that American facilities face identical vulnerabilities. The technology transfer concern extends beyond direct military applications to potential terrorist uses, as the same techniques that enable precision strikes against military targets could theoretically target civilian infrastructure or government facilities. Intelligence agencies identified at least 8 different organizations attempting to acquire similar drone capabilities within weeks of Operation Thunderstrike. Traditional military thinking assumes that defensive systems should cost less than the threats they counter. Operation Thunderstrike inverted this equation by demonstrating that inexpensive attacking systems could overwhelm defensive networks, costing hundreds of times more. Russian air defense installations at targeted facilities represent investments exceeding $500 million, yet proved insufficient against attacks costing less than most military vehicles. The total cost of Ukrainian drones deployed during the operation reached approximately $340,000, including development expenses, manufacturing costs, and operational support. This creates a cost-effectiveness ratio that fundamentally challenges every assumption about military economics and strategic deterrence that has governed defense planning for decades. The economics of modern warfare. These stark numbers reveal how Ukrainian forces have weaponized basic economics against conventional military thinking. Ukrainian FPV drones now achieve devastating cost-effectiveness against Russian armor vehicles, with $800 drones consistently engaging and destroying T-90M main battle tanks valued at $4.5 million each. The mathematical reality creates an economic weapon more devastating than any conventional military system because traditional cost-benefit calculations collapse when defending forces must spend thousands of dollars in defensive measures for every dollar attackers invest in offensive capability. Traditional military operations operate under completely different economic assumptions that Ukrainian drone warfare has rendered obsolete. A single Javelin anti-tank missile costs $175,000 and requires months of specialized training before operators achieve proficiency. Armored crews cost $180,000 to train over 18 months, while drone pilots learn in 2 weeks for under $2,000. The Javelin system requires complex logistics chains, specialized maintenance crews, and temperature-controlled storage facilities. Ukrainian drones operate from simple field workshops using automotive batteries and commercial spare parts available at electronics retailers worldwide. The Kursk Oblast operations in March 2025 provided the most dramatic example of economic warfare principles in action. Ukrainian forces deployed 340 FPV drones, costing approximately $272,000 total, against a Russian mechanized battalion containing equipment valued at $89 million. The engagement lasted 6 hours and resulted in destruction of 23 main battle tanks, 31 infantry fighting vehicles, 8 self-propelled artillery pieces, and 12 support vehicles. Conservative replacement costs for destroyed Russian equipment exceed $67 million, creating cost-effectiveness that traditional military planning cannot accommodate. Military planners trained in conventional warfare struggle to comprehend economic realities where defensive systems cost more than the threats they counter. Russian Pantsir S-1 air defense systems cost $15 million per unit and fire missiles valued at $70,000 each. Ukrainian FPV drones approach these systems at altitudes below radar detection thresholds, forcing defenders to engage with weapons costing 87 times more than attacking platforms. The economic mathematics become unsustainable when single defensive installations face attacks from multiple directions, requiring dozens of expensive interceptor missiles. Cost-effectiveness calculations extend far beyond immediate hardware expenses into training, maintenance, and operational logistics that multiply economic advantages. Ukrainian drone operators complete effective training programs within 30 days at costs under $2,000 per person. Maintenance requirements further amplify these disparities as Ukrainian drones use commercial components that mechanics can repair with basic tools, while Russian armored vehicles require specialized facilities, certified technicians, and proprietary spare parts. A drone jammed a resupply convoy once, halting 8 Russian tanks without a single shot fired. Ukrainian planners specifically target high-value assets that create maximum disruption per dollar invested, amplifying economic effectiveness through strategic target selection. The destruction of a single Russian command vehicle forces entire battalions to halt operations while communication networks are re-established and replacement equipment is transported from rear areas. Successful drone operations generate multiplier effects that extend costs far beyond immediate physical damage through operational disruption and resource reallocation. These operational delays consume additional fuel, require extra personnel, and expose support elements to follow-up attacks. Insurance and replacement cycles create additional economic pressures that traditional warfare calculations overlook.